Good morning. So this is the 8th lesson, and we are missing to finish the implementation of the binary heap. So during this lesson we basically conclude that implementation, and we will probably, but not for sure, introduce a new argument. Since many of you had problems in producing the make file, I want to go through at the very beginning, go through the process to produce it. So let me first of all perform again the steps required to produce the make file, and then you will see everything should be working as expected. So let me go to the code here, and I will oh, by the way, again, as usual, can you send me an acknowledgement through the chat, just to know that you are there? Thank you. So this is a terminal, just like the one you may have in your system, and here I'm inside just let's say downloaded, just cloned version of the repository. Hi there, hi. And so how can I produce the make file? Well, it's rather simple. If you have had already installed cmake, and you can download it from cmake.org, then by writing cmake lists, this is the command, and pressing enter, you will end up with all these writings, and this is it. So this is the process to produce the make file, and some other files, to be honest. In particular, so let me reset the terminal just to clean up everything we saw, and let me see what's inside my directory. You end up with a make file here. Okay. There are one more directory. This is a new file. This is a new file. But I mean, the really important things for us is this one. Okay. And so to compile it, your software, you simply have to write make and then press enter, and this is the result. Okay. This is it. So if in your system the behavior is different, please let me know, and I'll try to fix the problem, because of course giraffa giraffa to you, because of course there are many kind of systems on the wide, so it's quite difficult to figure out all the possible problems you may have. For instance, one of your colleagues yesterday was trying to compile all the software by using a compiler of 2015, which is a quite old compiler. So we were able to let him compile the code, but of course at the very beginning, I wasn't considering the fact that some of you may use such an old compiler. So the problems can be solved, but of course you have to let me know what are the problem. Okay. So just to let you know. Okay. Now we were at the. So we already implemented build heap. We already implemented so extract min. We already implemented epify, and we have already implemented decrease key, basically. Okay. And the last time we were trying to test whether the test delete min test was working, and we discovered that it wasn't working. During the last lesson I thought that it was a problem due to the fact that the code wasn't finished, but then just after the broadcast I ended, I figured out that there should be a bug somewhere, and I was able to discover it, and to be honest, the bug was this one. Okay, so at the end of let me just squeeze this stuff. At the end of build heap, we forgot to return the heap. So everything was fine. We built up the heap in the proper way, but we forgot to return the pointer to the heap itself, and so the heap is always empty. Okay, so let me fix this bug, and this is it. Okay, so now okay, let me just reopen the terminal just to do as you do. Now I'm able to compile again my code, and I'm able to execute test delete min, or at least I should be able to execute it. Okay, the code isn't already completed because we are still missing the insert function, insert value function, and the print heap function. We are still missing, but for sure the first test can be executed properly. Okay, so this is an indirect way to say that our code works as it is meant to work. Okay, here you can notice the difference between using binary heaps and arrays. So this test basically keep decreasing the size of the data structure. So start by having n elements and keep decreasing the array of data structure, always deleting the minimum among the elements on the data structure itself. Of course, the deletion for the array is virtual, meaning that once I found the minimum among the elements of the array, I simply swap the minimum with the last element of the array. I decrease an index which keep tracks of the virtual size of the array. Okay, so this column, so the column whose head is on heaps, basically keep tracks of building the heaps starting from the array, and keep removing the minimum until the heap itself is empty. Okay, so the time here is also for building the heap, not only for keep decreasing it until it is empty. So in some sense it would be expected to have a much faster result for the array, because here we have an overhead due to the fact we are building the heap. But of course, since extracting the minimum on the heaps takes time, which is logarithmic, if you remember, with respect to the number of elements in the heaps itself, the execution time of destroying, emptying, let's say, the data structure in this way, the binary heaps in this way, is much faster than doing the very same things on arrays. Okay, this is more or less the result. So you can try to plot these results. Of course, this is the results on on my laptop. If you try to run this very same test on your systems, you may end up with different results, more time, less time, doesn't matter. Just take the results and try to plot it by using I don't know, Excel or LibreOffice or whatever you want. Okay, so take a spreadsheet and try to plot this result, seeing whether what's the growth in terms of execution times with respect to the size of the input. Okay. Oh, by the way, of course this is not the execution time for one single instance of this problem. Actually, this is the execution time for 100 instances of this problem. Okay, so 100 arrays of natural value. I think natural values, but I'm not sure of it. Just let me check it. I don't know. No, floating point number. Okay, so at the very beginning of the computation of this test, basically we are allocating 100 arrays whose size is reported in the first column of the table, and we keep performing the deletion until all these on each of these elements, on each of this data structure, until the data structure itself is empty. Okay, so as I said, try to plot this table on any kind of spreadsheet to see what is the difference in terms of growth between these two objects. By the way, here you can also see that from time to time there might be some inversion. So here you can see that for 14,000 elements we spent 0.87 seconds, while for 16,000 elements we spent less. Okay, it may be the case because, of course, while you are performing your code, while you are executing your code, your system is doing many things. So it may be the case that you are downloading something. It may be the case that your Dropbox is performing some kind of operation. It may be the case your operating system is making some kind of weird operation. So it's not that strange to have a situation like this one. Okay, this is it. So okay, so let me answer one of the questions I just received. Would be noticeable difference in time for array if the type was okay. So one of your colleagues is asking whether there would be difference in time for arrays. Well, different in time if the type was int instead of float. Well, I don't think so. So probably there shouldn't any difference in time. There shouldn't be any difference in time by changing the handle data type from float to int. I don't see any reason to have differences, but of course if I run twice the very same test on the very same system, I may end up with different results. Okay, so and this is due basically to the fact that as I said, your system is doing many things. So so it could be the case that during one execution you have many tasks to perform, while during the next execution there is anything to do. okay? And so there shouldn't be any significant difference, but of course if I try to change on the fly the type, I may end up with different result. And by the way, let me run again the test just to show you that there should be, there may be differences. So I stopped the test just after the third line to show you that here we are getting different results, for instance, okay? But again, it's quite normal, it's not really relevant, and what we are interested in is just the trend. So we are interested in seeing the trend of our execution, of our execution time, okay? And that's the important thing, not the execution of the solution of a single instance of the problem. We are interested in seeing how well our code scale with respect to the input size. This is it. So let's again move to the code, and let me leave all your consideration about this piece of code, and let's try to conclude our implementation. So we already implemented the decrease key. Now we are left with the insert value and print heap, which is basically the last function is just a way to see what's going on. Okay, we want simply to print out our heap and see whether the heap, how the heap is built. Okay, just for debugging, let's say. So okay, so first of all, let me complete the insert value procedure. So just to avoid the bug we saw at the very beginning of our lesson, let me remove the return. So I'm sure to change it. Okay. Now, of course, since we are dealing with an array-based implementation of the binary heap, once we have reached the maximum number of elements in our array, in our array, so in our heap, we cannot insert any further value. So the first thing to do is to test whether we already reached the maximum size. So maximum size, if the max size, well, if the number of elements is equal to the max size, then return null. So the number of elements inside our heap is already equal to the max size of our heap. Okay, of course you can try to, well, by using the API we decided to use, it's not possible to change this behavior, because of course the array A is provided from as a parameter. So the array in which we store the keys is provided as a parameter of build heap, so is a reference from an external array, and so we cannot change its size. But of course you may try to implement a different version of the library in which you basically keep copying all the elements from the array A passed to build heap. Let me see here. So you may implement a different version of our library in which you basically allocate a new array. You copy all the elements you are interested in from this array to the new array, and then at this point you may grow up the array by allocating new space and copying the old array in the new array. Okay, but since we don't want to deal with all this stuff, we are only interested in finishing this implementation, and we don't want to allocate new memory for storing the keys of our heap. So this is the only possible behavior for our for our code. Okay, so every time we end up in a situation in which our heap already contains the maximum number of elements it can be contained by it, well, we do nothing and return null. Okay, so so if this is not the case, of course we have to insert the value. We have to create a new node, insert the value in it. Okay, and if you can remember, basically this is done by create a new node, inserting the maximum among the values in the total order, and then decreasing that values to this value. But the maximum is stored inside, so let me go to the data structure, inside the member max order value. Okay, so the max order value contains the maximum among all the values dealt, which are at some point inserted into our binary heap. And so the first thing to do before adding a new node is for sure testing whether the last maximum value, max order value, is greater than the value itself. Okay, because if this is the case, we can use the decrease key function, otherwise we cannot. So if this value is greater than the maximum value stored in our member, we cannot use the decrease value to insert this new value. Okay, but in that case we may assign this value to the maximum value. So let me write the code here. So if it's not true that value is smaller or equal to its max order value. So if this is the case, value is greater than the max order value, so we may copy it. So let me write memcopy into its max order value. We want to put the value, and of course we need to copy a number of bytes which correspond to the key size. Okay, this is more or less what we have to do. But doing this operation in this way, we are missing one basic case, which is the one in which the heap is empty. Okay, so say if before executing this operation the heap is empty, the value contained by max order value doesn't mean anything, of course. So this operation, so the operation of copying in max order value the value, should be also performed if h, so let me do it this way, h number of element is equal to 0. Okay, so if the number of element is equal to 0, or the value we want to insert is greater than the maximum value recorded by this member until now, well, we simply have to copy the value we want to insert in the maximum order value. So now for sure this value, the value contained by our member, is the maximum value considered until now by in our computation. Okay, now after this we of course have to allocate a new well, not allocate, but take compute the address of new node. So let me write new address, new node, okay, well, new node address. This is equal, so let me go up just in a way. So this will be the address in the array A of the new node. So the address of the key of the new node, basically. So let me write, okay, new node address. This is okay. And of course, this will be address of H number of element. Okay, why? So let me go to the slides. Here we have the slides. Okay, so so the first thing to do, so once we have decided which is the largest element considered until now, we have to insert a new node. The new node must be inserted as the leftmost node in the last level, if the level is not empty, or of course the leftmost node in a new last level, okay? And the position in the array of this node is the last one, basically. So the position of this node in the array, if we are dealing with an array-based representation of our heap, is the number of elements. Okay, so this is 0. I'm using the index in the C style, say C programming language style. So this is this key is stored in the index 0, this key is stored in the index 1, this is stored in the index 2, 3, 4, 5, and this should be 6. And as a matter of fact, you see the blue nodes are 6 in number. Okay, so that's why in our code we are getting this position as the address of the new node. Of course, then of course we need to copy the value we want to insert, well, to copy the maximum value seen till now, so the max or the value inside this position. So new node address H max or the value, and of course again since the values, we consider value as size, key size, the number of bytes I need to copy is key size. Okay, now okay, so in this way I'm basically doing the let me see here. Okay, doing this operation. Okay, so I'm assigning to the new node, I'm assigning not the infinity, but of course the maximum value that I consider until now. And what I need to do here, well, of course I need to increment the number of elements in my heap. Okay, this is it. Okay, so what are we missing now? We are missing to decrease our so decrease the key of this new node, because now it's max order, but it may be the case that our value is smaller than max order, and so we have to decrease that value, and this is done by calling the decrease key function, which takes the heap, a pointer to the node, to the key of the node we want to decrease, and this is basically new node address, and the value we want to reach, and this is value. Okay, and this is it. Nothing of particular. So let me just comment the code. If the heap is already full, and here if the new value is greater than let me write in this way, max, greater than max order value. Okay, of course, and here we are basically getting the position of the last node, of the new node, increase the size of the heap by 1, of course, and decrease the key of the new node. This is it. So let me see. Oh, you cannot see the code, of course. Okay, here we are. Okay, sorry. So here you can see basically what we did. We tested whether the heap is already full. We tested whether the new value is greater than max value order, or of course if it is completely new because our heap is empty. In that case, we assign value to the max order value. So we updated basically max order value. After that, we need to get the position of the new node, and since we are dealing with an array-based representation of our heap, the position of the new node is the last one in the array. Okay, and well, not in the full array, but the last one in that initial fragment, in the considered fragment of the array, which is the initial part, the beginning of the array. Okay. After that, we need to copy the maximum value already considered by this heap inside the new node as a key, and increase by 1 the size of the heap. And by doing this, we basically built a new node, insert as key infinity, and then that's all. So we needed to decrease the key of the new value, and this is done by the decrease key function. Okay, that's it. So missing heap, so printing heap. So what can we do here? Let me see. Well, we can do things in this way. Unsigned int next level node is 1. So this is meant to store the stores the index of the leftmost node of the next level. Okay, and this would be useful to know. So I want to print the heap by level. Okay, So the first level will contain exclusively the root, the second level the children of the root, the third level the children of the root, and so on and so forth. So by maintaining the index of the first of the leftmost node of the next level, I will be able to know where I should print a new line, basically. Okay, so if I reached the next level node, at some point the computation, if I reach the next level node, I know that just before printing the node itself, I need to print a new line. Okay, and of course I also need an index reporting unsigned int node equal to 0, reporting the node I'm dealing with. Now, let me see. Well, let's do it in the easiest way. So we can do it in this way: int node minus smaller than age, number of elements, node plus plus, and this is a way to go through all the nodes. And if node is greater or equal to next level node. So as I said, if at some point, well, let me write in this way. So if at some point I reach the next level node, just before printing the node I'm considering, I need to print out a return, a carriage return. So a new line characters, not a carriage return. So let me write printf infinity, and of course I need to update the next level node variable. And so if I'm in a if I am in the leftmost node of the next level of a given level, I can compute the leftmost node of the next level as the left child of the previous node. Okay, so if node has reached this variable, so this node is the leftmost node of a given level. Okay, so I can compute the leftmost node of the next level. This will be the left child of node. Okay, quite easy. Now if this is not the case, so if this is not the case, I'm printing a node which is not the first node of that level. So I want to separate this node from the previous one by using a tab. Okay, this is it. And okay, now how can I print a key? Well, of course, since we don't know the type of the keys inside our binary heap, I don't know how to print it, but we can use the key printer function, which is a function which is basically meant to print a value of the type of our binary heap. So if I write key printer and I pass as parameter address of each node, I end up in, what's going on here? wrong. No. Well, we will see. Okay, and this is a way to compute. So, giving a node, I can compute its address on the array A, and once I've computed the address of the node, I can print the key of the node itself. And oh well, this should be of course done inside the print, the for loop, and I think this is all. And let me print again a new line at the end of all the process. This is it. Okay, any question? Oh yeah, I discovered the point. Yeah, that's true. So let me now try. Some of you told me that the node variable was undefined inside that scope because previously was outside the for loop, and that's why the compiler, well, my IDE was complaining, but I mean wasn't really a problem. Now let's try to compile our code. And here, okay, some of you is asking what's address, sorry, addr, and this is a macro we defined during the very first lesson, which is basically meant to compute a pointer inside our array A. So if you remember, our binary heap stored the keys inside an array A, okay, and we need to compute the address inside our array A of the key corresponding to a given node. So how can I discover the address of the key of the node I can use this macro. And this macro, basically, since we are swapping the elements on A, they are ordered. Basically, this macro is a way to perform an operation like this one, okay, which, however, is not defined on A. Is not possible on A simply because A is a pointer of void. So we don't know how many bytes we need to skip to get the next element on the array itself. And to avoid to write all the operation all the time, we basically define these macros. Okay, so this macros is meant to get the address of the key corresponding to the ith node of our heap. And this is it. So let me try to compile it. As we already saw, we got well, let me compile from here just to, okay, and we got an error, which is this one, and this error is due to the fact, and as you can see here, the compiler is really nice because it's saying me, look, you are missing this header, and so we have to add the include standard input output header. Okay, so the complaining of the compiler is related to the printf function, which is undefined basically, but since it's quite standard, this function, the compiler already know that its definition is included in standard input output header. So he suggested me to include the standard input output header inside my code, and that's why I have added here. And so now let me reset and recompile it, and everything seems to work. Okay, The address intended as position in the memory, right? So yes, the address is a position in the memory, but I mean, is not, you are mentioning, someone of your colleague is mentioning as a decimal value, but it's just a number. I mean, when you perform an operation just like so take the ith element of an array, you are basically trying to see the element in a given position in the array. If you imagine the array just like an array, just like a sequence of subsequent elements, just like in this case, okay, and you know that each element takes, I don't know, 4 bytes, for instance, just to give you an example, okay? Okay, so how do you know, how can you know where the 4th element of the array, so this is the 0th element of the array, this is the 1st element of the array, this is the 2nd element of the array, this is the 4th element of the array. Well, it's quite straightforward how to get the position of the 4th element of the array. You simply have to take the first position, which is A. A is the pointer to the very beginning of the array, and you have to sum up A to what? To the ith element, which is the element you want to access, multiply by 4. Why 4? Because 4 is the space due to each element in the array itself. So if you change the space required by each element, you end up in changing this number. And that's why in our macro we do this stuff, the size, okay? Why? Because we know that we don't know the size of, we don't know the type of the element stored in A, but we know that each element in A takes time key size. Okay, and by doing this operation, I end up with the exact address, so the exact number corresponding to the very beginning of the value I want to handle in this at that point. Okay. So if it is clear, please let me know. If it is not clear, just let me repeat this stuff in a different way. Otherwise, I thought that you already know what's the meaning of pointers and why we use this macro. Because I mean, it's straightforward once you know that an array is just a pointer, and to get the ith element of the pointer, you simply have to perform this operation. And at the beginning of this semester, I gave a pre-course on programming languages, and I don't know what else. But if you go to that course, probably you would find any piece of information you need to understand why we are performing this kind of operation. Okay? Please say something, otherwise I don't know whether you understood. Say okay, say goodbye, say giraffe. Okay, so while I'm waiting for your hack, let me go on. So now finally we concluded the implementation of our code. As you saw, let me repeat. Now I'm cleaning up all the project by performing my clean, and so let me reset the terminal just to see exclusively what's going on right now, and let me recompile it. The compilation seems to work perfectly. So of course, by implementing the insert min and the insert value and the print heap, we haven't changed anything in the test delete bin, so we are left to test the insert program. So let me test it. Let me reset again the terminal, test insert, and see what's going on here. We get the difference value of that address, I guess. I mean the difference pointer. So someone is asking, by using ACK we get the difference value of that address, I guess. But I don't know what you mean by difference value of that address. What do you mean by it? It's just a number. It's an address. So reference from what? Whom? I mean, it's just a number. We are not interested in anything around that number, around that address. We are interested exclusively on that address. So before that address could be, I don't know, and after that address could be, well, for sure after that address you will find, so from that address on you will find the key of the node you want to deal with, but from that address plus key size on, we don't care. Okay, maybe again part of the array, maybe anything, but we are not interested on it. Yes, okay, it points to that cell of the memory. Yes, of course. So the address is a pointer pointing at that cell of the address of the memory. Man, the difference, I mean, I get the value stored inside that address. No. By address, I mean address. So you get a pointer to that address, not the value itself. Okay. So one your colleague is asking whether by using address I get the values stored in the array A, but this is not possible because you don't know the type of the array A, so you cannot handle directly the value. Okay, so the array A is a pointer to an array of void, so you don't know how to handle the number, the bit inside that array. You only know that you can chunk basically that array in pieces whose size is key size. Okay, and you know that every key size byte you have a new value, but you don't know the value itself. You don't know how to handle, you not even know the type of that value. And that's why this implementation is quite powerful, because you can, by using this implementation, you can handle floating point number, integer number, or whatever you want. Okay, even I don't know, more complex data structure, classes, or whatever you want. I think this is more or less clear. So let me test the test insert program. As I told you at the very beginning of this trip on the binary heap implementation, this function basically give you the chance to insert element in a pair of heaps and remove element from a pair of heaps, and this keeps going on until you end up with an empty heap. Okay, and these pairs of heaps are a min heap and a max heap of integers. And why integers? Since our binary implementation is binary heap implementation is general, well, because at some point I must instantiate this library, and this is done in the main file, in the main function of the test insert code. Okay, so in the main function of the test insert code, at some point I'm saying, look, I want to deal with a heap of integer, So let me see where we are dealing with it. Okay, here. Okay, here I'm saying I want to build an heap. The space for the heap is max A. I'm getting at the very beginning of the computation 0 element from A, so the heap at the beginning will be empty. The max size, the maximum number of elements in the heap will be max size. The size of the elements in the heap will be size of int, and the total order I want to use for the max heap is greater or equal on integer. Okay, this is the moment in which I'm saying I want to deal with a max heap containing integers. And as a matter of fact, you may see that you may have noticed that looking at the previous line that actually, oh well, this is a bug. Let me fix the bug. Okay, float. Sorry. Oh, let me save it. Okay. Okay. As you saw, as you may have noticed from the previous line, here actually we are allocating space for a pointer to floating point numbers. Okay, but this actually doesn't matter. Doesn't matter because we are passing max A as a pointer to void. So the binary heap library doesn't know that this is actually a pointer to float. Okay, and handle it just like it was a pointer to void. Okay, so let me go on with the test to see whether our code works or not. And I've just run test insert. Let's try to insert the number 3. So by inserting number 3, we end up with 2 heaps. A max heap in which we exclusively have 3, and of course 3 is the root. A min heap in which I have exclusively 3, and 3 is the root. And we may insert, I don't know, 5 for instance, just to test it. And as you can see here, we have now by inserting 5 we end up with a heap having exclusively 2 elements. The max heap, in the max heap, of course, the root contains the minimum with respect to the total order, which is actually 5, because the total order is greater or equal than or equal to, while the min heap, in the min heap, the minimum is of course is 3. Okay, keep inserting, so let's say -7, and as you can see here, we end up with prop handling of the new node inserted. So in the max heap, the new node is basically a child of the root. In the min heap, the new node value is inserted as root because it's the minimum among all the elements in the heap itself, and so on and so forth. So if I keep going on, I end up with what you may expect. Okay. Now by writing 0, I can extract element from the heap, and of course I will extract at each step the minimum, exclusively the minimum, because we can only extract the minimum from a heap. And here we are dealing with the max heap, and by extracting the minimum, of course, I end up with an heap in which we are missing the value 15, while on the min heap we are missing the value -7. Okay. Going on, again, we remove from the max heap, we remove the maximum value, which was stored in the root and was 5. From the min heap, we remove the minimum value, which was 3 and was stored on the root, again and again. Okay, so this is just to show you that our implementation of binary heaps seems to work as expected. And let me see. Okay. And this is pretty much all we need to implement a binary heap. Okay. Now, as a homework, I asked you to. You may find, by the way, you may find all the material, including the homeworks, the slides, and so on and so forth, on the description of this video and of the former video and of the former video. So you may also find the homework for this lesson, which asks you to slightly change the code and try to figure out a way to avoid to swap the element from the array A. Okay. If you remember, at the very beginning of our talk, we were mentioning the fact that it is possible to avoid to really swap the elements on the array A, and this can be done by basically keeping in memory, let's say, two new arrays, telling you which is the position of the key on A for a given node, and which is for a position in A which is the corresponding node. Okay, and so as homework, I ask you to change the code we saw here and try to implement a version of this library in which you do not swap the element on A. Okay, and this new implementation will be really helpful for something we will see later on. So it's mandatory to have it, let's say, in a few lessons. Okay, that's it. So if you don't have any more question on the code, please. So if you have more question on the code, please let me know. Otherwise, I will move to the next topic. Any question? Okay. So let's move on to the next topic, which let me do in a while. Okay. Oh. Sorry. Yes. What's going on? Okay. So okay, so the next topic next topic will be a new argument, will be retrieving data and sorting. Okay, So let's see something really useful. So let's assume to have some kind of data in an array. For instance, I don't know, patient records. Okay, each element in the array is associated to an identifier. For instance, social security number, or I don't know, or codice fiscale, or you know it. So how can we find the data corresponding to a specific identifier? Well, a possible solution is quite straightforward, and is the solution to scan all the array, so all the database, for instance, searching for a possible position in which the identifier is equal to the identifier we are searching for. Okay? And what's the complexity, asymptotic complexity in terms of big O of this naive solution? Well, the asymptotic complexity of this naive solution is, of course, big O of n. Okay? Why? Because we are required to scan all. We may be required to scan all the array to get at the correct position. Even if we assume, even by assuming that we know that value is already present, is for sure present in our array, it may be the case that the element corresponding to the ID1 is present, is the last element in the array. So in that case, we are forced to scan all the elements of the array, and that's why the complexity is big O of n. Now, can we do better than this? Well, for sure we can, otherwise I'm losing time in talking about this topic. And how can we do better? Well, just figure out how you search for a given page inside a book. Okay? N. What do you mean by n? Oh, okay, what's n? N, I see your point. N is the size of the database. So if we are storing our database inside an array, the asymptotic time required to scan all the array, of course, is the size of the array itself. Now, how can we improve this strategy? Well, of course, you can figure out a possible new strategy by observing that when you are searching a page in a book, you basically open the book in the middle, see whether that page is the page you are searching for. Otherwise, if it is larger, you may focus on the first part of the book, or focus on the second part of the book. And you keep repeating all this operation until you end up in the correct page. Okay, this is the strategy, and this strategy is called dichotomic search. So let's assume to have A ordered. Okay, so if A is ordered, so the array is ordered, we can do as I just said. So is ordered, of course, with respect to the IDs. Okay, so we can look at the element in the middle. If we discover the correct ID, then we are done. Otherwise, look whether the ID of the element in the middle is greater than the ID we are searching for. And if this is the case, we focus on the first part of the array. Otherwise, we focus on the second part of the arrays. Okay. And okay, let me go back to something I just saw on the chat. At some point of my presentation, I was asking what's the complexity of scanning the whole array, and some of you answered n. Well, n is not a complexity. Okay. Well, it's a function, of course, but the complexity should be given in terms of big O notation. So big O of n would be a correct response, because we don't know whether going through each element on the array takes time 1, of course. So a better response, a better answer for what is the complexity of going through the array would be big O of n and not n. Okay, just to clarify. So I was saying the strategy is open the array in the, so we have the array already sorted with respect to the ID. We search, we look at the element in the middle. If the element in the middle is the one we are searching for, we are done. Otherwise, we compare the ID of the element in the middle with the ID we are searching for. If the ID of the element in the middle is greater than the element we are searching for, of course we have to focus on the first half of the array. Otherwise, we need to focus on the second half of the array. Okay, and we have to repeat all this operation until the part of the array we want to deal with is empty. If at some point the part of the array is empty, we know that that element, so ID 1, is not present in our array. Otherwise, sooner or later we end up with the ID. And this can be easily proved simply by observing that if A is already sorted, for sure, at each step, either I discover an element, the element I want to end up with, or I'm focusing on the set of the element which contains, for sure, the ID I'm searching for. Okay, quite easy. So just to have an example, let's assume to have I want to let me remove the ID condition and simplify the problem by looking at searching an element inside an array, which by its own is not really interesting, but give you the chance to understand what's going on without avoiding the useless details. Okay, so searching for 2 in this array, which is already sorted, is quite simple. First of all, I need to focus on the whole array and search for the middle element. Now the middle element is in position 5, because I'm dealing with 10 elements. 10 divided by 2 is 5, and the value stored in the position 5 is 5, again 5. Okay, now 5, of course, with respect to 2 is greater. Well, 5 is different from 2, so we haven't found we haven't found the cell we're searching for up to now, but of course 5 is greater than 2, so we need to focus on the first part of the array. Okay, so once we have discovered that 5 is not the number we are searching for and 5 is greater than 2, we can forget the last part of the array and focus on the first part of the array. Again, here we can easily, so we are considering 4 elements here, the elements from position number 1 up to elements position number 4. So by taking the middle element, which is 2, okay, we may detect whether 2 contains, so the element number 2 contains a value equal to 2, but this is not the case. So again, by checking whether 0 is greater than 2, we decide that we are not interested in the first part of the array, but we are interested in the second part of the part of the array we are dealing with. Okay, so we move to focus on these 2 elements. Why these 2 elements? Because in the previous step we decided that this is smaller than 2, so for sure the elements we are searching for should be after this value, since we are dealing with an ordered, assorted array. And so right now we are focusing on this part of the array. Now what what next? So again, I must take the middle element. Since I'm dealing with two elements, the middle element will be the first one, and so this is it. And again, I must test whether this value is equal to 2, but this is not the case. So for sure, the number I'm searching for is in the last part of this focus. Okay, so this for sure should be here. But again, I'm not completed my task because at the moment I haven't found the 2. Okay, so to find 2, again I have to compute the middle element of this focus, which of course is 4 because I'm dealing with just one element, and this is the middle element, and finally I discover that 2 is in position 4. Okay, so these are the steps I need to perform to find 2 by using a dichotomic search in an array. Now have a look. Let's have a look to the code, and let me just see what's going on here. Okay, let me just have a look to the code. Okay, so here we have okay, let me instead of having a look to the code, let me write it, which probably is much focusing. So let me move to tablet. Okay, and this is it. Okay, so now we have to write an algorithm for dichotomic search, dichotomic find, and we want to find the index corresponding to a value v in our array. Okay, so first of all we may need to define two variables. Let's call them left and right, which will store the left boundary of of our focus and the right boundaries of our focus. Okay, so at the very beginning we will end up with 1 and 8. Now, while we are dealing with a focus which is greater than 1, so while greater or equal to 1, greater than or equal to 1, so while right minus left is greater than 0, what? Well, first of all we have to compute the middle element in our focus. So the middle element, let me call it m, would be of course right plus l divided by 2. Okay, so this is the middle element of our focus, and so the first thing to do is to test whether our value is in m. So if a of m is equal to b, then return m. So if my value has been discovered, so if my value b has been discovered inside a in position m, I should return the index m. if this is not the case, so let me write and if and move to another let me write in this way, to another whiteboard. If this is not the case, we must test the value stored in AM and test whether it is greater than the value we are searching for. So if AM is greater than B, so if this is the case, for sure our value V should be stored in the very first part of the array, well, of our focus. So we have to update, so let me think, left, right. We have to update right, and right will be set to M minus 1. Okay. Let me see. Okay. Otherwise, for sure, we are guaranteed that AM does not contain V. So we need to update left because we are interested on the second part of the array, well, of the focus of the array. So left should be updated to M plus 1 and it. Okay, and this is it. So I can write and while. So going back to the previous whiteboard, so we see here that our execution keeps going until we end up in a situation in which the left boundary of our focus is greater. Oh, this will be greater or equal. Left boundary of our focus is greater than R, and if this is the case, we discover a situation in which V is not present in A, so we may return 0. Okay. So what's the meaning of returning 0? Since the indexes of A should be contained in the interval 1 n, so it should be positive natural number. By returning 0, I mean I haven't found the value V in A. And to conclude, and def. So this is the code for the iterative code for the dichotomic search in an array. Of course, this dichotomic search works exclusively for arrays containing values, but you may figure out a way to deal with different kind of comparisons. So as we did for the heaps, you simply have to change this relation and this relation, you end up with quite a general code for finding values inside an array. So you may imagine a situation in which you are dealing with an array of objects of very complex classes, and by instantiating this relation, you are able to search values inside these classes, okay, these objects, and this is it. So now, what's the complexity of performing all these operations? Well, this operation takes time, of course, theta of 1, we are doing 2 operations into 1, but it doesn't change very much. At each step here, so let me delete this one and this one. Okay, so at each step, so right, no, okay, right minus left. Let me delete this. At each step, right minus left is decrease by 1/2 of, no, writing in this way is, let me write in this way, is after okay. Why is after? Because at each iteration I'm basically splitting the array into 2 equal arrays. So so every time I'm taking the middle and I'm focusing either on the first part of the array or on the second part of the array. But I can be lucky, so it could be the case, I may be lucky, so it could be the case that at some point I may end here. So what? So since the complexity of each iteration is easily to see is theta 1, so each iteration costs theta of 1. So the total complexity is what? Well, is logarithmic, is big O of logarithmic base 2 of n. Okay. Why? Again, each iteration of the while loops takes time, which is theta of 1. How many iterations should I do? Well, at each iteration I'm splitting by 2 the focus, so keep splitting by 2 the focus, I end up in a number of iterations which is logarithmic with respect to the initial size. Okay, so the dichotomic search takes time, which is logarithmic in time, takes time, which is logarithmic with respect to the initial size of the array. So let me delete this and write in this way. Okay, and all this stuff can be found on the slides that I will provide you the next time. Okay, so going to the slides, here you are. That's pretty much all. So if you have any question about what we saw, please let me know. I will see your comment offline because the lesson should be ended right now. So if you have any comment on what we saw today, please let me know. If you have any doubt about the retrieving data by using dichotomic search, if you have any doubt about the complexity of dichotomic search, please let me know. Okay, these slides are not present on below the video, but you will find it I mean in 10 minutes probably. Okay, that's all. So see you on Thursday for the 9th lesson of this course. Stay safe at home and keep strong. Okay, again, if you have any doubt, please let me know. See you the next time then, probably, if I am. Okay, bye.